Welcome to part 3 of the analog monitor project for Arduino Uno using the Earth People Technology board. The final piece of the analog monitor project is the PC application. This application will fetch the data from the CPLD and display it on the screen. It includes user code, Windows form, and the active host DLL. So the active host DLL is designed to transfer data from the CPLD when it becomes available. The data will be stored into local memory in the PC, and an event will be triggered to inform the user code, written C# that data is available from the addressed module of the CPLD enter. This method from the user code on the PC makes the data transfer transparent. So the data just appears in memory, and the user code will direct the data to a text box on the Windows form. So the analog monitor project will perform the following functions. Find the EPT570AP device, open the EPT570AP device, start the Arduino data collection process, wait for the data from the EPT570AP, decode byte position, upper or lower, then display the data in a text box. So the C# project creation. To start the project, use the wizard to create a project called Analog Monitor. When the wizard completes the C# Express main window, we'll have all of the attributes set up. Next, click on File, Save, Project As, and go to the default location, which is Users, Username, Documents, Visual Studio, 2010 Projects. Then select a folder, Analog Monitor, and click the Save button. Locate the project's active host 64-bit active EPT Analog Monitor folder on the Uno Analog Monitor Project CD and copy the following files over: active transfer x64.cs, form1.cs, form1.designer.cs, form1.resx, program.cs, scale factor menu.cs, and then open up a Windows Explorer window and browse to Users, Your Name, Documents, Visual Studio 2010 Projects, EPT Analog Monitor, and paste the files to this folder. In the Solution Explorer window, back in the Visual C# Express, click on the project name, EPT Analog Monitor, and select Add Existing. And when the Browse button comes up, select the files activetransfer.64.cs, scale factor menu CS. Click OK. Next, the project environment must be set up correctly in order to produce an application that runs correctly on our target platform. Visual C# Express defaults new projects to 32 bits. If your OS is a 64-bit platform, use the following directions to set up a 64-bit project, otherwise you can skip the next few directions. First, we need to tell C# Express to produce a 64-bit code if we're running on the x64 platform. So go to Tools, Settings, Expert Settings, and select Show All Settings. Check the box by Show All Settings. In the window on the left, go to Projects and Solutions. Locate the Show Advanced Build Configurations checkbox and check that box. Next, go to Build Configuration Manager. Click on that, and then in the Configuration Manager window, locate the Active Solution Platform. Label, select New from the drop-down box. In the New Solution Platform window, click on the drop-down box under Type or select the new platform and select x64. Select the OK button. Verify that the Active Solution Platform does say x64, and then click Close. Okay, then using the Solution Explorer, you can right-click on the project, select Properties, and click the Build tab on the right of the Properties window. Locate the Allow Unsafe Code checkbox and check that box. Now we are ready to start coding. Go to Solution Explorer and right-click on the file form1.cs and select View Code. Near the top of the file, notice that we have a namespace and a class. The namespace EPT Analog Monitor is used to declare the scope of the project, and the class EPT Analog Monitor is used to organize our user code that we will write. Now, other classes can be used within this namespace and that we can declare, and their components can have different access properties. Next, we have two classes for our device. Now, one class stores the information useful for our device for the transmit to the end terms, such as address of module, length of transfer, or etc. The other class is useful to store data received from the end terms. You'll notice down at the bottom of this page that you have two objects: EPT received data, which is an object of the transfer class, and EPT transmit device, which is an object of the transfer array class. So that declares these two objects of classes. And if you'll notice, right underneath the public partial class EPT analog monitor form, there is a function EPT analog monitor. This is a constructor, and it's called immediately whenever you click on the .executable file. And so this little bit of code in here will be executed as soon as you click on that file. And initialize component is something C# requires you to do. And we've got a for loop that goes through and sets up each of the EPT transmit devices of an array of length I. That sets up several objects for us to use into the code. So next we set up constants for commands and end-term addresses. We'll set up variables to hold the current display address, first display byte, error correction, placeholders. These are for the error correction that we'll get to later on. Now the first function we come to is the load function. And this is the function that gets loaded up when analog monitor gets called. So this function is called automatically upon the completion of Windows form. So there's no need to do anything to call it. So once this function gets called, it in turn calls list devices. The list devices function calls the EPT open function to load up the active host DLL. Next, it'll call the EPT query devices, which searches through the registry files to determine the number of EPT devices attached to the PC. Next, the EPT get device name is called inside a for loop to return the ASCII name of each device attached to the PC. It'll automatically populate a combo box called CMB DEV list, which with all of the EPT devices, which will populate with all the EPT devices it finds. So the user will select the device from the drop-down box. This value can be sent to the open device function using the button click of the open button. Okay, once that happens, the device index variable gets the integer value from the combo box device list of the device that's been selected. Then it can pass that into the functions get device name and get device serial. And by doing that, we're going to get back a pointer to that device so that we can select it and use it and talk only to that device when we are sending out requests to the interms or receiving data from the interms that we want from that particular device. And so the rest of this code is just handles the error correction stuff. And then you can see at the bottom that the callback function is called there. This function can be called from the active host DLL. When the EPT devices transfer data to the PC, the callback function will do something with the data and the command, such as a byte transfer or block transfer or a trigger. And because the callback function communicates directly with the DLL, it must pass pointers from the DLL to the C#. We use this thing called marshalling. Now, marshalling is an advanced C# topic, and we're not going to cover it in this particular manual. We'll just let the callback function work in the background. We'll only need to use the EPT parse receive function to handle incoming data. We could see that easily in our user code. So next up are the controls, such as buttons and text boxes, are added to the form1.cs. This is the design part of this particular file. This will allow us to turn signals on and off using buttons, and the buttons include the button OK, button cancel, button open device, button close device, start, stop, set scale factor, and reset block. So we also add text boxes to our controls. These are the combo things like the combo device list, text box monitor 1 through 6. Now, something to be said about the buttons. Although the C# language is very similar to C code, there are some major differences. The first is that the C#.NET environment is event-based, and the second, of course, that C# utilizes classes. So event-based programming means that software responds to events created by the user. A button click or a drop-down box click. We will add a button to our example program to show how the button adds an event to the Windows form and a function that gets executed when the event occurs. The easiest way to add a button is to double-click on the form1.cs in the Solution Explorer. Then click on the toolbox button, and then grab a wait till the box gets populated. Then go down to where you see button. Just put your mouse click on that and grab it and pull it over into your Windows form. So once you do that, you'll go to the properties side and give it a name such as btn, open, and then maybe go up to the text and actually put some text in there, so you can just write OPE and open. Now once you're done with that, double click on the open button in the Form 1, and the C# Explorer will automatically switch to the form1.cs code view. The callback function will be inserted with the name of the button along with the underscore click appended to it. And then, of course, a parameter list also. And in that parameter list, you should see object space sender, comma, space event arg space e. These two additions are required for the callback function to initiate when the click event occurs. There is one more addition to the project files. Double-click on the form1.designer file in the Solution Explorer and locate the section of code. The code that has a bunch of this dot button open. This code sets up the button size, placement, and text. It also declares the system event handler. Now this statement sets the click method, which is a member of the button class of the button open device button. To call the event handler, the button open device click, this is where the magic of the button click event happens. So when you click on the button, this event handler is asked by Windows to call this button open device click function. So the button OK and button close buttons are used at the end of the application. It calls the function ept close by device index to remove the device from the active host DLL. At the end of each click event, the application exit method is called, which exits the form and essentially is a graceful exit out of the code. The button start and button stop buttons are used to start and stop the EPT570 AP USB transfers. They call the function EPT send transfer control byte to send the start stop control signal to the control register. And to do this, just give it an end-term address. So I'm using end-term 2 at the PLD. And then to start it, send a 1 as the data. And to stop it, just send a 0. Okay, and then there's a button for the set scale factor, which calls the set scale factor menu open window. This is going to be explained later. It sets up text boxes and buttons, labels at the runtime for use in retrieving the scale factors for each analog channel. Okay, so next up is and at the bottom there is the reset monitor buttons 1 through 6. These are used to call the text box clear method, which when invoked will clear whatever's in the text box. Okay, so next up is the EPT read callback function. So when an analog signal is received from the CPLD, the read callback is called and pass parameters from the active host DLL. It then calls the EPT parse receive function. This function uses a case statement to call the transfer out receive function. And the transfer out receive is the function that decodes the message, which will be an 8-bit message, selects the end term address, reads and stores at first the upper byte, then on the successive call it'll read and store the lower byte. When it gets the lower byte, it'll have the full 10-bit sample data, and at that point it will update the text box with the digitized values from the conversion. When a transfer message has been received from the EPT570 AP, the transfer out receive function uses the EPT receive data object address to conditionally branch to a set of statements. This is done using the switch case statement. The switch will select one of the case statements based on the collection of addresses, the transfer out address 1, transfer out address 2, all the way down to 6. Okay, so when the code enters the transfer out address, let's say 1 case statement for the first time, the display address 1 should be set to the same address as the EPT receive data dot address. Now that remember that EPT receive data is a class. It's an inherited class object with a class, and address is one of the parameters that gets filled up by the callback function itself. So the first display byte should go high. This will cause the first if statement to be entered. When it is entered, 3 things happen. The analog value is cleared to 0. This is done to clear out any of the value that was previously in there. The first display byte is set to false, so that the next time the case statement is called, the transfer out address number 1 is entered, the lower byte will be added to the first 8 bits of the analog value. So the 8-byte buffer EPT receive C-clock buff data is right shifted by 8 bits. It is then added to the analog value. This will store the upper byte from the EPT570 AP to the upper 8 bits of analog value. When the third statement in the if statement has completed, the case statement is exited and the thread is ended. Then again, the next time the read callback is called, the switch conditional is entered again. This time the EPT received data address will again be the transfer out address 1, and this time first data display byte will be low. So again, the first case statement will be entered. The second if conditional branch will be entered at this time. When it is entered, the following occurs. The write received char is cleared to 0. This is done to clear out any value that was previously in there. The variable is used to collect the modified analog value and send it a thread to be written to the text box. The first display byte is set to true, so the next time the callback is called, the transfer out address 2 is entered, and the upper byte will be added to the first 8 bits of the analog value, which effectively starts over the cycle over. The byte buffer EPT receive data clock C block buff 0 is added to analog value. This will store the lower byte from the CPLD to the lower 8 bits of analog value. The scale factor variable is checked for non-zero value. If it's 0, the analog value is converted to a string and stored in write receive char. If the scale factor is non-zero, the value is set to the result of analog value multiplied by the scale factor. So the results of scale factor conditional branch is converted to a string, then stored in write receive char. The next several statements update the display address, 1, 2, 3 variables. It sets the current display address to false and sets the next incremented display address to true. This is done so that the C# code can be synchronized with the code of the Arduino, and we've got some. This will also allow some error checking a little bit later in the code. Next, the write receive char value is sent to the thread that will populate the text box. Calling a thread is similar to calling a function. To launch our write to text box thread, use the parameterized thread start function. This allows us to pass an object, write receive char, directly to the function that's called by the thread. Finally, the text box TB monitor 1 is updated. This is done using the invoke method instruction. A method is just a function in a class, and the invoke method is a clean way of updating the text box from a different thread, so a different calling thread. So there's think of like an OR gate. You've got several devices wanting to update that text box, but they all need to ask the Windows operating system, can I access that text box, and that invoke method that's what does it. So once that invoke method has been called, the EPT transfer out thread is complete. The text box is updated with a 10-bit digitized sample from the Arduino selected channel. After that, this whole process repeats the above steps for the rest of the 5 channels. Okay, now let's explain the scale factor and how that works. It's in a separate file all by itself. So when the upper and lower bytes have been received from the EPT570AP, the analog value has the ADC counts from the Arduino channel. But this is just a digital representation of the analog signal sampled at the ADC input. To convert this into a real voltage, we have to multiply the raw counts by a scale factor. First, we need to calculate this scale factor. Should be this is accomplished by taking the full scale deflection of the ADC. This means the maximum voltage the ADC can take for the Arduino Uno. For the Uno, it's 5 volts. Then divide this number by the total number of counts of the ADC. For the Arduino Uno's 10-bit ADC, this is 2 to the 10th, and that equals 1024. So the scale factor is going to be 5 volts divided by 1024 counts. So our scale factor will be 0.00488 volts per count. To set the scale factor for each Arduino channel digitized value, we added all of the code to the file scalefactormenu.cs. That's one of the files that you copied over. So the top of the file declares the namespace to add the code to and the class that it belongs to, and both of these are of course the EPT analog monitor namespace and the EPT analog monitor class. So the code is activated when the user clicks on the scale factors button. So when it's clicked, the callback function calls the click event, and in there it calls the scale factor menu open window function. The code will expand the WinForm, meaning that it actually physically adds more size onto the windows, and adds text boxes, buttons, labels, all this done at runtime. The code looks the same as if we used the drag and drop method from the Visual Studio Toolbox. However, we just type it in by hand in this case. Okay, so to add a value into the scale factor X text box, we just type in a number in the key press event will be raised by typing into the text box. When the event occurs, we execute our code to retrieve the scale factor. When we execute our code, the scale factor is set equal to the string value of the text box, scale factor 1 text box dot text. This means that the number retrieved from that text box is in the wrong format. So we need to convert that string into a float value to be used as our scale factor. To do this, use the convert to double method, then recast the double as a float. So that it becomes scale factor 1 is equal to float in parentheses outside of convert to dot to double, and then in parentheses scale factor 1 text box dot text, and then in parentheses and put a semicolon out there. Then just to repeat this key press event for all 6 scale factor text boxes. So after the scale factor, there is a few synchronization and error correction conditional branch statements that's added to the transfer out receive function, but we're not going to go into detail on that, so it's pretty confusing stuff. I can explain that in the user manual better. So that is all the code that's needed for the Visual C# project. So next we've got to build the code. So building the analog monitor project, we'll compile the code in the project and produce an executable file. It will link all the functions declared in the opening of the analog monitor class with the active host DLL. The project will also automatically link the FTD to xx.dll to the object code. Okay, so to build the project, go to Debug, Build Solutions, and click on that. The C# Express compiler will start the building process. If there are no errors with code syntax, function usage linking, then the environment responds with the build succeeded. If the build fails, you will have to examine each error in the error list and fix it accordingly. Do your best to try to fix this stuff. Look for misnamed variables and misused variables and type errors, usually the most common. So if you cannot fix the error using your troubleshooting methods, post a topic on the Earth People Technology Forum. All topics will be answered by a member of the technical staff as soon as possible. So at this point, the environment has produced an executable file and is ready for testing. Next, we will connect everything together and see it collect some data and display it. Before we can run the code, we need to include our DLLs in with the folder that includes the executable. So what we need to do is to browse over to our project. We'll go to Users, Documents, Visual Studio 2010, Projects, go into EPT, Analog Monitor, go into the binary folder, hit x64 release, and you'll see that the executable is there. Now pull up a Windows Explorer window, go over to the CD where the Analog Monitor Project CD is, browse down to the project's active host 64-bit, go to EPT Analog Monitor, and go to the binary x64 release and copy the active host.dll and the ft2dxx.dll and copy them over to that project folder with the executable. So this is all that is needed for the analog monitor project. The Arduino will generate a 10-bit digitized word for each channel and then transmit that word to the CPLD using the write enable, address, and data pins. The CPLD transmits each 10-bit word to the PC using an active transfer in term and a one-hot state machine. The DLL reads the 10-bit word into local memory, then calls a callback function. Each 10-bit value is finally collected and displayed in a text box in the Visual C# code. So that's it for part 3. Next up is part 4, putting the whole project together and testing it out. So stay tuned. Thanks.